Okay, so we're going to take a look at fluid mechanics. And so for the first one, we're going to be dealing with finding the pressure at the bottom of a body of fluid. In this case, we're going to look at the pressure at the bottom of a pool. Now, what we've talked about in class, and I may not necessarily have shown completely, but I'm going to expand on this a little bit because this will be a pretty short problem so that we can see it a bit more clearly. Now, what we've done is we're going to look at a pool, and we're going to imagine that it's a very simple shape. It's just a square shape, okay? The way I'm drawing it. And this pool is filled with water and is going to be 3 meters deep. And we want to find the pressure at the bottom. So if we put something here, or if we're down at the bottom of the pool, swimming around, we'd like to know what type of pressure is actually we feel on ourselves there. So, in this case, the equation that we've been using in class is our pressure equals rho GH. This is the gauge pressure. If you want to use the more universal, our pressure at our given depth equals P naught plus rho GH, where P naught is the pressure exerted onto the fluid at the top. In this case, that's just atmospheric pressure. So often what we'll use is something called gauge pressure. And that's one where we're just seeing how much more pressure there is from the ambient, usually atmospheric pressure. This, my marker may be dying on me. I was hoping to get more out of them than just that, but let's see. This is often called absolute pressure. Okay? In this case, we're fine just finding the gauge pressure. That's the main thing that I'll be asking for in general. I will try and make markings as to whether or not I want gauge or absolute, but if I don't mark it, then you're safe to assume that I'm looking for gauge. Okay? In this case, we'll plug in our values. The pressure at the bottom will be rho. Well, that's rho of our fluid, density of our fluid, which is going to be water, which we're going to treat as 1,000 kilogram per cubic meter, times g, we're near the surface of the Earth, so 9.81 meters per second squared, times h, how deep are we? We are 3 meters down. When we run these numbers through, we find that the pressure that we experience is 29,430 pascals. I apologize. That is the gauge pressure that we feel. For the absolute pressure, we would have this term, so we would just add in atmospheric pressure, which is 101,325 pascals, so we'd add that on to that and we could find what the absolute pressure is. But one of the things I want to look at real quick, let's assume that we've got our pool and it is shaped exactly like a cube. And that it is 3 meters by 3 meters by 3 meters. That's a horrible bracket, but it means well. And we're going to have it filled with water. So basically, we're going to be looking at 3 meters by 3 meters by 3 meters of water. Well, the volume of water is going to be, since we're dealing with a cube, that's going to be 3 meters times 3 meters times 3 meters, which comes up to 27 cubic meters. And what I'm going to do is, I'm going to show you a relationship on where this type of equation comes from, why we can just find the pressure at the bottom to be rho GH. And what we're going to do is we're going to look at a whole body of water in a volume that we're familiar with. So we know this total volume of water that we have there. If we want to find the weight of water that we have there, you know how heavy it is, we're going to take 27 cubic meters times the density, which is 1,000 kilograms per cubic meter. times, that'll give us our mass, because that's our volume times our density, which will give us our mass, times the acceleration due to gravity. And this gives us effectively mg of the water, so we know the actual weight of that large mass of water. We end up with that mg of the water comes up to, let's see, 264,870 newtons. Turns out it's pretty heavy. 27 cubic meters of water is actually a lot of water. All right. What I want to know now, so I can imagine that that is the weight, the force, the normal force being supplied by the ground beneath it, right? Because to hold that much weight up, we've got to supply enough to hold it, right? Newton's second law. So if we saw this just as an object weighing that much to hold it up, to keep it from accelerating downward, we'd have to supply equal and opposite of that force. Just like we often find that the normal force is equal to mg when we have no acceleration in the y direction. Well, the same thing should apply here. Okay, so the normal force being applied by the ground has to be equal to this. And so we've got a force applied over an area, the bottom of this pool. Well, the bottom of the pool is nothing more than 3 meters times 3 meters. That gives me 9 square meters, right? Okay, well, I know that my force is equal to 264,870 newtons. I know my area is 9 meters squared. And so my pressure, which should be force divided by area, should be 264,870. Hopefully I'm not going out of the frame here. Divided by 9 meters squared. And I find that the pressure associated with that, surprise, surprise, comes up to 29,430 pascals. The same as over there. Now the way fluids work, we can actually find it doesn't matter how big the bottom is. You can see that to get that force, that total amount, we had the volume go in there. 3 times 3, well, then later we divide 3 times 3. So all we're left with is this guy, which we could imagine is our height. And we could go through and we could derive it fully, but the important thing that I want you to see here is we can still see where these values are coming from, just thinking about it in our old Newtonian mechanics way. But in this case, because of the way fluids work, we can actually ignore most of how big the actual vessel is. All that matters is how deep we are in it. And so that's because pressure is force per unit area, and so the bigger we make it, well, we're just adding in more terms of area, but we're also adding a lot more fluids based on that area, and so they cancel out. And all that we have to worry about is our height.